Small town, southern land. This is happening, yeah. Face to face with greatness and a stranger. How does a moment last forever? How can a story never die? It is love we must hold on to. Never easy, but we try. Sometimes our happiness is captured. Somehow a time and a place can stay. Love lives on inside our hearts and always will. Minutes turn to hours, days to years stand gone. But when all else has been forgotten, still our song lives on. Maybe some moments weren't so perfect. Maybe some memories not so sweet. But we had to know some bad times, for our lives are incomplete. And when the shadows are ridiculous, just when we feel all hope is gone, we'll hear a song that no one's heard. A love lives on. Last forever. How does our happiness endure through the darkest of our troubles? Love is beauty, love is pure. Love is no mind to desolation. It looks like a river, song, protects, receives, and perseveres, and makes us whole. Leads us to hours, days to years, still gone.
You getting in the honky tonk, Hunter?
Yep. I switched to country in like 2004 because pop was annoying me. Now I just listen to musicals and all that stuff. Sorry. I figured it'd be boring when I sit here and stare at you guys, so that was my iPhone on shuffle. You're welcome.
Yeah, Dr. Carr does the same thing for safety, but he has like this weird elevator jazz music.
I was like, I'm gonna see what pops up. We had Hamilton, Prince, and Blake Shelton. So it's a variety here. All right, we're finally getting into actually doing concrete. I know we're all excited. Let's do. So what I was going to do today was, first of all, ask if anybody has any questions. Let me share my screen. Where'd my thing go? Oh, just share screen. Do this every time. That's fine. We don't need a camera. So this is the basis of most of reinforced concrete design. This slide right here. We assume a strain distribution within the section where we have compression on one side, tension on the other. It's linear between the two. We assume a stress distribution of the concrete and that the stress in the tensile reinforcement is a certain value. We'll go back and check it. And we resolve those stresses into forces, solve for equilibrium, and then go back and make sure that what we assumed was right. So does anybody have any questions about that? Any confusion?
To be honest, I haven't started the homework yet, so I'm sure once I do that, I'll have questions. But
Okay.
out of the example you worked, it was pretty.
Okay, good. So my other thing I was going to do, I was going to show that example, and then I was going to start another example that is similar to the last homework problem. It's in your book too, but it's a test of the principles, basically. So let's see. So we did that. That's my little how to do it. And there is the example. So we write equilibrium. We assume, we assume some things like we assume our steel is yielded so that we can use the yield stress of the steel, which is 60 KSI. We studied equilibrium to solve for the depth of the stress plot, which is related to the depth to the neutral axis by that beta 1 factor. Then we go back and make sure once we found that depth of the neutral axis that we have yielded our steel, which is okay if you haven't. I mean, if you want to, but you just have to redo your calculations then. And then from there, we check our minimum steel and calculate our nominal capacity without the P factor on it. And that is where we stopped. So any questions about that process if you guys followed along? So I was going to work this example. And I want you to know this was my exam problem in my reinforced concrete, this type of problem. I'm being nice to you guys. I'm not giving it as an exam problem right now. You're welcome. So if you guys want to copy it down first, I don't think I put it up there. I forgot to include it. And we'll start working through it. So what do we know? We know our F prime C, right? That's our compressive strength, 3,000. Our yield stress of our steel is 60 KSI. And our area of steel is, we have 3 number 8 bars. So I have 3 times the area of a number 8. Anybody want to guess what that is? Look it up.
0.79.
Yep, 0.79. Right. Again, that's one you might end up having memorized at some point. So our area of steel is 2.37 inches squared. Let's see, we need to know our beta 1 factor that relates the depth to the neutral axis to the depth of the stress block. So 3,000 psi has what beta 1 factor? Anybody got their AC after 18?
Be 0.85.
Right, 0.85. That's from that table on page 399. The tab. What else do we want to know? So what's different about this one is this is going to be, when we resolve our compressive stress into a force, we need to know the area over which it happens, right? And usually if you're talking about a rectangle, the area over which it happens is the depth A and the width of the beam B. But now our compressive stress block is going to be a triangle. I did make an equilateral triangle, so the width is the same as the depth. So my area of my stress block, my compression stress block, right, is 1/2 the base times the height. Like the base of that triangle A. If I look at this is straight out of the book, but if I look at my strain profile, I'm still going to assume that the very tip has a compressive strain of 0.03. That's the maximum compressive strain. Maximum compressive strain of concrete. That line needs to, that's my steel, right? My depth of my steel. And that my steel, which is luckily all in a line, we're going to assume it has a strain equal to or greater than the yield strain. So that my steel has yielded. This dimension, that's the depth of the neutral axis, C. If I make that into a stress, right? I have my compressive stress acting on this area, whatever it is. And the height of it is A, right? That's what I just said right here, A, which is equal to beta 1, C. And I have this stress in my reinforcement equal to the yield stress. Stress in my concrete is 0.85. Pausing for a moment to make sure everybody's not. I feel like I'm going fast. So far everything is the same as before, right? I have an assumed strain profile and assumed stresses. Where it gets different than a rectangular section is I want to resolve those stresses into forces. So I have a stress, a compressive stress, acting over this rectangular area. Or compressive stress acting over the area. If I want to resolve it into a force, I need to multiply the stress, the pressure, right, which is 0.85 F prime C. That's the pressure. And the area is 1/2 A squared. Usually that would be 1A times B, right? But it's a triangle. The other question is, where does that resultant act? For a rectangle, it would act right in the middle, right? Look up here. So it would act at A over 2. But for a triangle, I need to go to the centroid of that triangle, which is at 2/3 of the height, which is A, so 2/3 A. On the tension side, on the steel, I have my tension force T, and it doesn't change because I have my yield stress multiplied by my area of steel. So this is the strain and the stress profiles are the exact same, regardless of the shape of your B. They'll also stay the same if we add steel in the compression part. What's changing now is we're just making it a funky shape. So that's just going to change the area over which that stress occurs. So instead of A times B, we have 1/2 A squared.
So that C equation in blue, that's what you're going to set equal to FYIS, correct?
Yeah. The T, this is my tension force in the steel, which is the yield stress, because I've assumed my steel has yielded, times the area of the steel, right? A stress times an area gets you a force. This C up here, this is my resolved compression force in my concrete, which I assumed had a magnitude of 0.8, the stress had a magnitude of 0.85 F times C, and the area is over a triangle. So it's 1/2 A squared, but if it was a rectangle, like in the example that I did on the video, it would be A times B, because it'd be happening over this rectangle. B being the width, right, of the beam. This is a cross section. This is this is a triangular beam. It's like a big giant Toblerone, right? I don't know. So, if you guys know what that is, let's check. So that is, you don't have to draw this profile every time. It might help, especially when it starts to get a little bit more complicated, but that is the profile and the resulting forces. Any questions so far?
Well, I was 10 minutes late because I didn't get the Zoom invitation. So I'm just wondering what page you're on.
Oh, it's on something that I didn't give you guys. So take a minute and copy it down.
It's on what?
It's this page right here. I didn't give it to you guys.
Oh, it's one of the blank ones.
Yeah, I forgot to include this in there.
Okay. I'll just screenshot it.
Okay.
Oh, wait, I don't know. Never mind. I don't know how to do that. I'll copy it down. Take a picture of it with my phone. Gosh.
I was like, I can email. I can't email it to you because I'm on my.
Okay, we're good.
Okay. So we're just doing, this is just applying, instead of using a nice rectangular cross section, we're looking at something funky. This is going to help on the last problem of the homework. So. Okay. So my next step is I'm going to set C equal to T. Because my cross section has to be in equilibrium. So I have 0.85 F times C, 1/2 A squared equal to AS FY. I guess this is also, I should probably say that's the C sub 0 for compression in the concrete. There's never tension in concrete, but there could be compression in steel. So if I look at this equation, I know F prime C, I know AS, I know FY. The only thing I don't know is my A. I'm going to solve for that. My area of steel was 2.347, 2.37. Yield stress is 60 KSI. I'm going to put my F prime C in KSI so that I can just cross them out. So 3,000 PSI, so it's 3 KSI. Should get a value of about 10 inches. Is that right?
Okay, so for rounding on homework and stuff, you want us to go to 1 decimal, or I typically go to 2, doesn't matter.
That would be fine. I mean, this is kind of an intermediate calculation. So I would actually probably even keep that number like in my calculator and then move on. Like,
Yeah, I do. So your final answers, though, I guess you just want to the nearest KSI.
well, yeah, well, because this is, our final answer is the nominal capacity.
It'll be in what, kip feet then, I guess?
Yeah, kip feet. So probably kip feet could be, you know, if it's like, probably have a 1 decimal point. Kip inches, probably not, because those are going to be bigger values. You know, it's going to be like 4,500 kip inches. You don't need 4,500.2. You know, where it's like more about sig figs, I guess, than, you know, like 3 sig figs, 3 or 4 sig figs. I don't know. But yeah.
So you really don't care, just make it accurate.
Yeah. Yeah. Yeah, I'm one of those people that I write big long equations and solve for the last problem, like the very end. So I don't need to round things along the way. But so yeah, so right, our KSI cancels out KSI, square root of inches squared, that gives me inches. So that's the depth of my stress block, 10.6 inches. The whole thing is like 24, so my stress block is probably like that whole. All of that much of it is in compression. Makes me a little nervous because the more of it is compression, the less likely you're going to hit your strain, right? Right? The bigger your stress block, the bigger your C value. So it's going to be down here. So your strain might be like that. So that might not hit yield, is what I'm trying to say. But we'll see. Because that's my next thing to do. I figured out the depth of my stress block. So now I'm going to check my assumption
Do we
that,
not have to calculate C before that, or no?
well, we're about to do it, yeah. Yeah, you can't get away, you have to calculate A and B, or A and C, but I'm gonna do it right now. Right. So I assumed, I'm just gonna draw this again, you don't have to if you don't want to, but right. I assumed a strain profile. No matter what, this is always going to be 0.003. This distance right here is the depth of my neutral axis C. This distance here is the depth from the extreme compression fiber to my centroid of my steel, which is E. What I want to know is what's my value of the strain in my steel. So I can calculate, right? A equals beta 1 C. So C equals A over beta 1. I got 10.6 inches divided by 0.85. So the depth of my neutral axis is 12.4. It's like halfway down. So I can use similar triangles to solve for my strain in my steel. I think I wrote this down in the notes. Right. ES over this distance, D minus C. That's one triangle. Right, because these angles are the same. Is equal to the ultimate strain in my concrete divided by C. And the strain in my steel is strain in my concrete times V minus C. 0.003 times D, which was 21.5 inches. Two one nine two two, however you rounded it. So 10 decimals, just yes, please, 10 decimals. No, don't use 10 decimals. I will kill you. So I'm going to ask the question: did the steel yield?
Can you scroll back up a little bit, please?
Oh yeah, sorry. To there.
Yes.
Okay. Tell me if I can slow down. I just
We haven't finished yet, so we can answer that question, right? Don't we have to calculate EY? Should
Oh,
be FY over 20.
Yeah, that's what. Yeah, can you calculate what the yield strain would be and compare it?
well, for
Yes.
60 KSI, it's always 0.00207.
Right. Yeah. I'll give you guys
Where's
a couple more minutes because it sounds like I went too fast for some people.
No,
Sorry.
I just missed one thing.
Okay. Okay. Can I go back down?
Yeah, you're good now.
Okay. 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 Please yell at me to slow down if you need me to.
where's that AS min equation in our ACI book?
Page 135.
Oh.
And it's down at the bottom of the page, and I literally have it written turn page because the second part of it is on the next page.
Yeah, I had done that from your video, but I forgot to mark it, so I couldn't find it.
Okay. That's fine. Yeah, so if you start to, because after a while you might remember that for 60 KSI it's 0.0207, but let's just remember it. EY is my yield stress divided by this elastic modulus of steel. So 60 KSI divided by 29,000 KSI should be that. So I just barely yielded, but I did. All right. Yes is greater than EY. Right. And since I yielded, that means I can use the yield stress Fy. I don't have to go back and redo any calculation.
So can you talk through again what we would do if you didn't yield? What would, you'd have to go back and recalculate FY?
Yeah, it would. And I'm. Is it bad that I'm trying to remember? I think it's you have to do an iterative process because you have to guess it. Like you have an A, like your A that you
How do you
calculated.
recalculate a given though? FY is given to you.
Yes, but that's assuming your steel has yielded. If your steel hasn't yielded, then the stress in the steel is not Fy, it's something slightly less. So I went up here and I calculated this A in my equilibrium, assuming that the stress in the steel, right, my tension force is really the area of steel times the stress in my steel. Since I'm assuming it's yielded, I'm assuming that's Fy. If the steel hasn't yielded, then the stress in my steel is going to be something less than that. So I have to go back and calculate a new A. Like in this instance, I would use this, or in that instance, not this instance, but okay, I have a strain. From that strain, I can calculate a stress. I'll go back and put that stress in here, recalculate an A, and iterate until I have a depth of my stress block corresponding to the right yield, or not yield strain, right strain and stress in my steel. That's why we like it when it yields, because then it's a simpler calculation.
Yeah, that sounds terrible. Let's not do that on a test.
I wouldn't do that. Well, I don't say I wouldn't do that on a test, but
So it don't make you angry, right? You could.
so we haven't done any examples that way yet, so I wouldn't make you do that just yet. But also the ultimate goal would be that you want it to yield, because then your attention controlled section, right? Because if it hasn't yielded, then you might fail in compression first, meaning you're going to have a more brittle and a more sudden failure than a ductile failure. So that's all good. That's why we want this to happen. Now, obviously, a concrete column, you know, the steel is going to be in compression. But a beam, it's not going to be. So our question now, so we yielded our steel, so we can go, we can check that we have the minimum amount. This is really something that is more appropriate when we're on the design side, but it's good to get that check in there. Right now, all we're doing is something's already designed and we're making sure it works. So on page 135, good tab to have is our AS min. That's the maximum of 3 squared F times C over Fy times the width. Or 200 over Fy. So really, you need to figure out if 3 square root F prime C is greater than 200. But the maximum, like 3 times the square root of 3,000 psi. And I'll say it every time. When your F prime C is under a square root, it has to be in PSI, and the answer comes out in PSI. It makes no mathematical sense, okay? But, but it is what it is, right? And the width, well, this is a variable width, right? We have a triangle, but it would be safe to assume the maximum width is conservative. You could use an average width, but we can use the maximum width because that would give the highest value. So the width is 12 plus 12, 24 inches. And my depth is 21.5 inches. Same thing here, 200, again, that's in PSI, even though it doesn't say that in the thing. So my minimum steel that I need to have based on the dimensions and the material properties the maximum of those two values. And my AS was 2.37, so I'm good there. Greater than 1.72. Anybody have any questions about that one? Just write in your manual if you want to remind yourself about the units. Does weird, funky stuff. Now, what they actually asked us to do was calculate our nominal capacity. And my equation for that is I need to just, all right, I have this force couple. I have a compression force and a tension force, and I need to take the moment about one of them, right? The force couple caused the moment. It's nicer to take the moment about C sub C because there's a lot less variables in the tension, at least right now. So I need to know the distance, right? The distance between the two, which is D, the whole overall distance from the extreme compression fiber to the centroid of my steel is 2/3 times A. Or the whole distance is D. I need to subtract that 2/3 A. That's the moment arm between that force couple. So if I take the moment about the C sub C, it would be my nominal capacity is T times that moment arm, which is D minus 2/3 A, or AS FY D minus 2/3 A. So my area of steel times the stress in that steel, which is the yield stress, so 60 KSI. The moment arm, which is D, 21.5 inches, 2/3 A, which was 10.6 inches. 3.7? Yeah, 3.7. Making sure that I got the right number. Got like 20.2052, something like that.
Dr. Turner, can you go back for a second, please?
To which part?
Get done with this. To the last part, before you went to the screen.
Mm-hmm.
No, where you were drawing on the diagram with the couples. Oh, thank you.
Mm-hmm. So if you're following along in the textbook, I found an error with their units. They have pound inches and it is kip inches, right? Because if I have kips per square inch, that goes away, that goes away. So it's kips times inches. And if I divide it by 12, 171 kip. So the only difference between this weird section and like a nice rectangle, like the equations that we gave before, I'm gonna go back to here. Strain profile is the same, stress profile is the same. The resultant force, because the area over which it happens changes, the location of that force, because the centroid of that area is different than before. As a result, it changes some things, but the principles are the same, right? It's still 0.85 F prime C, but the area, instead of being AB, is just this 1/2 A squared. The location, instead of A over 2, is 2/3 A, because it's a triangle. As a result, it just means a slightly different equilibrium equation, right? And a slightly different moment arm. That would be D minus A over 2. Now it's D minus 2/3 A.
So did you use 10.6 in your calculation, or did you use the full number?
I use 10.6. Yeah.
So that's why I'm asking, like I would have got 4K or 4 kip inches more because I used like the full number for A.
That's okay. Yeah. You
Make
don't have
something
to
like
like
10 digits all you want. It makes a difference, don't it?
but I mean, what would that be like?
Still
Yeah,
rounds to 171 kip feet though.
yeah, 2058, or is that what you got?
I got 2056 and some change.
2056. Right, divided by 12, it's still 171. Like, and if you're that close on like your, you know, if your maximum moment that you need to carry is like 2059, like maybe you should change some stuff, right? Because well, not only that, but we're gonna multiply this by phi next. That's gonna be the next little video to watch, because that's what you have to do on the homework too. Because the phi factor varies depending on if it's tension controlled or compression controlled. But yeah.
Yeah, I was following an example in the book, and I guess it used a equation for transition, which I wasn't sure what that meant, but
Yeah,
I
there's
mistakenly
like,
used that equation
if you're at a
first.
certain value, it's this. If you're at a certain value, it's this. And in between, it varies.
Does that just mean it has tension and compression going on?
Um, yeah, it's, where is that P factor? If you turn the page, where's the picture of it? 394. It's like one of them's definitely controlled by the compression, like the failure of the concrete. One of them is definitely controlled by tension. And then in the middle, yeah. And that's all just based off of like experimental stuff. Right.
You said we're gonna have to watch, I guess, another video before we complete the homework.
Yeah,
It's due Monday, right? So I
yeah.
guess just over the
I'm
weekend.
gonna post that. So I need to do it, but I'll post it tomorrow. Okay. So does anybody have any questions about all this that we haven't answered yet? These are this like I've said multiple times. This is seriously like concrete right here. This little profile stuff. So you're gonna get familiar with it by the end of the semester. And like I said, this was actually on my concrete exam, and we'd never done an example like it or anything. So it was super fun. Like a let me just test your learning, right? Well, that's all I
I
have.
totally would have used the equation for a rectangle, and I would
Yeah,
have thought I was right too.
yeah,
And the one in the homework isn't an equilateral triangle, so it ends up being a little weird there.
yeah. That's true. Yeah, yeah. You gotta figure out an equation for the width versus the depth. If you guys get all the way down to the end and just find the nominal capacity, like, don't, that's fine. So, yeah. Okay. Well, if you guys don't have any other questions, I can let y'all go start working on the homework. It's really fun. Yeah. I like concrete a lot. Maybe because it's mechanics. I don't know. That's just me. I liked it better than steel. I feel like there's less randomness. Well, I guess I will let you all go. Have fun. Have a good afternoon.
Bye.
Bye.